Hi, folks. My name is Nick Matzke. I'm co-authoring this talk with my PhD student, Wallis Bland. Although all complaints should be directed to me, I'm mostly responsible for the argument here. This talk is entitled A Statistical Comparison of DEC and DEC+J is Statistically Valid. And I'll say a little bit at the end about a path towards a more statistical sophistication and realism in phylogenetic biogeography. All right, so I apologize for having to record this meeting. In New Zealand, I work at the University of Auckland, and it's 1:50 a.m. when the talk occurs, and I have these two cute little kids, and if I wake them up, I'm in big trouble. So could I please ask that if there are any questions, please somebody save them. If they're in the Discord app or something, maybe they're just automatically saved, or email them to me. I'm happy to answer them at some point online this week. Thanks. All right, so this talk is about the comparison of two models in biogeography, which are quite well known. I'll only give the briefest introduction. There's the DEC model, which is dispersal extinction cladogenesis, and a stochastic mapping example of that model is on the left. So possible collection of possible histories of the Psychotria Hawaiian shrub clade, which is a common example data set used for these historical biogeography programs. And this model is on the left, and you can see that this model postulates a lot of possible widespread ancestors. Is the typical pattern you get with the DEC model. DEC+J is a model that I invented, which simply modifies the DEC model to add the process of jump dispersal, which we'll talk about in a minute. And you can see that the histories that are proposed under that model tend to be simpler and tend to be a history of island jumps, for example, in this island data set. We can calculate log likelihoods to measure how well these models fit, and the DEC model gets about -34.5, and DEC+J gets about -20.9, and this is about a 300,000 times improvement in model fit. Founder event speciation, which is this +J process, this jump event. Here's sort of a conceptual view of what it might mean. It's just the idea that a new small population founds a new population in a new area, jumping across a barrier, and it's basically instantly genetically isolated and soon would develop characteristics that would lead to be called an isolated gene pool or a new species. We don't have to postulate any special mechanisms like punctuated equilibrium or anything. All we need is this idea that occasionally you have long distance allopatric speciation at whatever scale that you're looking at. Basically barriers are crossed and a new population is founded. Is that process important? Should it be included in our computer models of biogeography? That's the fundamental question that we're thinking about here. My position, right, I've taken this, it's pretty clear. I do think we should use statistical model choice in biogeography. And for example, we should compare models without founder event speciation and models with founder event speciation. All right, folks have probably seen this slide. This is an explanation of how different programs make different assumptions about what processes are allowed. And in particular, one thing that I was drawn to when I got into this area was that a lot of the traditional models like DIVA and DEC just left out founder event speciation. They had allowed various kinds of vicariance or subset sympatry, but they just disallowed founder event speciation. And I thought, hey, why don't we put that in a program and see if it improves model fit? One study that folks may have seen is this one of Solanaceae, the tomato family. And just briefly, we can do things like allow geography to change through time, weight different kinds of dispersal based on distance. And we can propose a whole bunch of possible biogeographical models and include things like jump dispersal and distance as possible explanatory parameters, and then use likelihood and AIC weights to judge which models fit the best. AIC, right, never tells you the true model, it just tells you which model is the least bad fit, right, or the closest relative distance to the truth. The assumption of AIC is that you never actually have the fully complex true biological model. That's basically impossible in science. We're just looking for better approximations. All right, and with these tools in biogeobears, you can do things like do stochastic mapping to get a statistical sample of dispersal events of all the different kinds, and do things like measure how much dispersal out of South America and back into South America was there. So this was Dupin et al. 2017 Journal of Biogeography, just to set us up. This phenomenon of DEC+J having a big advantage, a big statistical advantage, it is very common. right? In my initial paper, Systematic Biology in 2014, I looked at this in a whole bunch of clades, and almost all, but not all clades showed this advantage, often, pretty ridiculous improvements in log likelihood and AIC. 10 or more log likelihood units was quite common. And even comparing a whole bunch of models with and without jump dispersal, so a DEVA-like model and a Bay Area-like model, in addition to the DEC model, right? The +J models tend to dominate in these kind of island data sets. Now, this phenomenon has become so common that I think a lot of people were just skeptical that a single parameter could improve model fits so much. And I think some people have just had difficulty accepting that. I did point out, I tried to point out at the time, and I've been pointing out ever since, that it is not always the case that J improves the model fit. There are a few data sets where DEC plus J does not have an advantage over DEC. And I even issued a beer challenge for a while to ask people to find data sets that didn't do that. Turned out I found one that didn't have an advantage for DEC plus J over DEC. So here's one, Tagetes butterflies. This was cited in Matzke 2014. I've cited it in many talks. So it's a fallacy to assert that jump dispersal always provides an advantage. There's some kind of intrinsic advantage for the plus J model. Some data sets, it's not the case. And here's one where it's not. You'll notice that all of the species, many of the species have widespread ranges. That's a key point. All right, so of course, what I'm addressing here is this critique that's been published by Richard Ree and Isabella San Martin. This critique is from a few years back. It was in the Journal of Biogeography, and it said a variety of strong claims, like there's degenerate likelihoods when comparing DEC and DEC plus J, and that there's pathological consequences of degeneracy, right? Those are strong words. This paper has been influential, right? It's been cited over 250 times already. The authors are distinguished leaders in the field. They're editors at the Journal of Biogeography. They're major authorities in the field. And the paper is now very often cited to justify, to just run DEC and ignore the DEC plus J model, and not even to do statistical model comparison in terms of log likelihood or AIC weights. Most of the citations, when you look in the literature, they're pretty critical. Some of them are kind of agnostic, but they sort of say like, there's a debate, who knows, but we're going to be, we're just going to not run this model comparison because it's under dispute. So anyway, this paper that I've got here, Matzke 2021, it's online at OSF. The point of this paper is to convince you otherwise. All right, so go read this paper. This talk is an advertisement for this paper. All right, here are the main points that I make in this critique of the critique. I say statistical model comparison is identical to the comparison of two ClaSSE submodels, and it's therefore valid. And I make a number of other points, including I'm going to show that the log likelihoods in the critique are wrong. The examples that they show of counterintuitive inference are tiny examples, and they're brittle. The Biogeography's likelihoods do properly add up. There's no anti-DEC bias. I point out the true source of the DEC plus J advantage, and I show how ClaSSE is directly comparable to the DEC and DEC plus J models by adding a Yule process to those models. All right, so let's back up first. I think this critique got way more attention than it should have, actually. I think maybe people should have stepped back and thought a little bit more before accepting the advice of the critique. And it's just based on basic principles of statistical model comparison. They say a DEC-based model may be defensible if statistical model selection is not used to justify the choice. And I think everyone should have said that, what's going on there? That should make us go, because if you take that advice seriously, this advice, it would make biogeography unique in the world of phylogenetic methods and unique in inferential statistical science. It would basically say you can pick models without ever looking at the data, is what the assertion would be there. Statistical model comparison is not a rare thing. It's used in tens of thousands of papers. AIC is used in tens of thousands of papers across dozens and dozens of fields. It's actually not exactly optional to just say, well, we can use it or not. You need some method of measuring how well your models are fitting the data, and the standard ones involve likelihood. Either they're Bayesian methods that involve likelihood, or they're AIC or some version of penalized likelihood. Even frequentist methods fundamentally rely on likelihood. All right, so I've made that point here. Burnham and Anderson, the sort of Bible of statistical model comparison with AIC. It's got over 50,000 citations. It's actually a problem for the field of biogeography if we all decide that we can just go do something different. We're kind of operating in defiance of the rest of the statistical inference world. All right, and of course, anyone who's done phylogenetic comparative methods or DNA model selection, chosen GTR models over Jukes Canada models, you've all used AIC and statistical model comparison already. So you've already accepted it if you're basically in the field of phylogenetics. So can biogeography really be different is a key question. All right, the critique does make some specific claims. It claims degeneracy in the DEC+J likelihood optimizations, and it does show two examples that I have confirmed do give weird inferences, right? They have two examples where is shown in this figure here. The log likelihoods optimize at sort of the maximum J value where you get an all jumps kind of inference. It's not quite all jumps for some specific reasons I mentioned in the critique, but it's J hits its maximum value and it's a data set of size 2 or of size 4, giving this behavior. And a lot of weight is put on that. This is these are given as examples of pathological inference. But before we address that, I want to point out some things. They claim to have a worked example of why this occurs, but actually the log likelihoods are wrong in this critique's worked examples. I replicated their data sets, ran them. I actually ran them in Biogeobers and in Lagrange, which is a program that Rick Ree, one of the critique authors himself, wrote. Biogeobers and Lagrange agree on what the log likelihoods are. The critique's worked examples don't. In one case, I could figure out what went wrong in their calculation. In the 4-taxon case, I couldn't. You can read all about it in the critique, but either way, somebody should have ran this on the actual program. And if they had, they would have had to double check their calculations. I'm surprised that nobody has done it until little old me comes along to do it. But it's kind of a significant point that if we're going to make claims about likelihoods, we should at least have the right likelihoods from the correct models. All right. I do get their degenerate inference, or their sort of, it's not degenerate, it's just unintuitive inference on small data sets. So you can see the top curves in each of these plots represent their 2-taxon example, and you can see the maximum likelihood inference of J is at the maximum value. It's not exactly 3, but just below 3 was the maximum allowed value. But what you should observe is that as the number of species increases, we get what you should expect in a likelihood analysis, which is as you get more data, you get a peak closer to a reasonable value. Okay, so as we up the number of species, we go to 5, 6, 7, 8, 9, 10, we start to see a second peak develop that's not at the maximum value of J. And pretty soon we get a J that you would expect with, one species living in area A and a bunch living in area B, which is kind of the way they've set up that example. You get a very reasonable low inference for the J value. And this applies in a whole bunch of different examples. Basically, their 2 and 4-taxon examples are very brittle and don't hold up under a range of modifications. All right, but we should have never taken a 2 and 4-taxon example as a serious example anyway. We don't test methods in phylogenetics with sort of tiny human constructed examples. We use simulations. We would use AICC if it was a tiny data set, and if you use AICC on these examples, you don't get the DEC+J advantage. I did thousands of simulations in Matzke 2014 to verify this DEC+J comparison. These simulations were totally ignored in the critique. It's quite surprising that nobody has pointed this out. All right, we can in this article that I've written, I show that the fairness of the DEC and DEC+J likelihoods is easily verified. Short version of this table is you can calculate likelihoods for all possible data sets under a given set of parameters for DEC and DEC+J, and for both models across any set of parameters you like, across all data sets, all the log likelihoods, in this case of 8 possible ranges. All the likelihoods across all data sets, they add up to 7.0. And that's because in a 3-area problem, you have 8 possible ranges. One range is the null range. It's an impossible ancestor, so the log likelihoods add up to 7. This proves that the log likelihoods are fair, they're accurate, and that no specific model has an advantage. It's just certain models are favored by certain data sets and other models are favored by other data sets. which data sets you see in nature is an empirical question. That's not unfairness. That's just science, right? All right. The true source of the DEC+J advantage is not this claim that's made in the critique about time, exploiting time independence of cladogenesis. The true reason is simply that the DEC model needs intermediate states. To explain single area ranges, the DEC model has to postulate ancestors living in multiple areas. And so any simulation you do on inferred DEC parameters will have to have a bunch of ancestors living in multiple areas. And when you have that, you're going to have a bunch of tips living in multiple areas if that simulation is the process that's running. If you have a data set where most tips live in single areas, then that DEC model is just going to fit poorly and it's going to be statistically inadequate. And that's why it fits poorly. And any model that can improve on that, like DEC+J, will fit better. If you have a model that predicts states that you don't see, like widespread ranges, and you don't see widespread ranges on a particular data set, then that model won't fit well. That's just science. That's not a bias. All right, here's some slides showing that. I should keep moving here. But yeah, statistical inadequacy is easy to show for the DEC model. And it's easy to show that if you infer under the DEC model and do simulations, you'll get a lot of the branches will occupy widespread ranges for much of the branches, and many of the tips will come out widespread. So whereas under DEC+J, you get many fewer branches living in widespread ranges, and many fewer tips will come out living in widespread ranges. So if your data set looks like that, then DEC+J will have an advantage. All right, so this has nothing in particular to do with time independence. The critique makes a large deal out of time independence, but actually we can create, in addition to the refutation I just showed you, we can create time dependence by just adding the likelihood of the tree under a Yule process. You wave your magic wand, add the Yule process likelihood. Now your cladogenesis processes are all time dependent. Doesn't change the relative. You add the same constant to both a DEC model and a DEC+J model. It doesn't affect the model comparison. So this time independence point is actually irrelevant for the DEC+J advantage. All right, and I can show that in another way. And I have a script in the critique, and as well as this figure. We can do calculations of likelihoods under ClaSSE, under basically doing a submodel of ClaSSE to create the assumptions of the DEC or the DEC+J model. And then we can calculate likelihoods under DEC and DEC+J, and we get essentially perfect correlation between the log likelihoods. Essentially, the log likelihoods under the ClaSSE model differed from the log likelihoods under the DEC or DEC+J model by a constant. Now, that's not all ClaSSE models, right? Those are two specific ClaSSE submodels. ClaSSE, right, is the cladogenetic state-dependent speciation extinction model, which is recommended by Rhee and San Martin in their critique as being a valid model. But comparing DEC and DEC+J is just identical to comparing two special cases of the ClaSSE submodels. So the critique endorses comparison of ClaSSE submodels, but that is the same thing as comparing DEC and DEC+J, so the critique refutes itself. And I think it should be considered basically dead at that point. Now, there are some legitimate critiques of DEC+J. This use of relative weights, the J parameter is kind of arbitrarily set between 0 and almost 3. You can convert those to rates through time just by multiplying the relative weight of each event by the speciation rate. But it's easier in the computer to use this weight strategy, but it does create a little confusion for humans. Another big flaw that is real in these models is that DEC+J and DEC, they both ignore extinction. This is a big limitation which could be fixed by using ClaSSE models. But there are some big hurdles here. One is that accurate inference of extinction is a problem across most of phylogenetics. It's a huge problem to accurately infer extinction, even if you have a model that can include it. And then secondly, the ClaSSE models have to iteratively solve these large systems of ordinary differential equations. And the biggest one I've ever seen is about 50 states, but often in biogeography, we have about 1,000 or more states. So there's a huge technical hurdle to cross there. My lab is working on it. We may get progress there, but it's quite a challenge. All right, so I think I'm out of time. Just here's some thought questions for you. This critique has become influential, but as I've shown, there are many mistakes. They're all documented. All the scripts are in that preprint that I've put online. The article's in peer review now. But why were none of these mistakes caught? A lot of them could be demonstrated simply by taking example data sets and running them. I feel like the critique has been cited without a lot of people checking any of the assumptions or stepping back and thinking about what are we doing with statistical model comparison. Another point that I make in the paper is the DEC model somehow the default? Does that make any sense at all? If we had 10 different biogeographers and then 10 different models, would they all be similar to the DEC model? I kind of don't think so. And, then there's this ubiquitous advice, all models are wrong, but some models are useful. Even if we do get to use ClaSSE models for realistic biogeography analyses, they're going to have to make all kinds of simplifications to work, and so the question is always comes down to what approximations are acceptable, and how should we tell? And I think we should tell using statistical model comparison, the standard method used in dozens and dozens of fields by tens of thousands of scientists. And I don't think biogeography is any different than any other field in that way. And so we should rely on statistics and not on tradition or verbal arguments or authority. And we should, using those methods, we can look to the future. And I've put a few slides in of future work that we're currently working on. All right, so thanks very much. And I will stop the recording